Good morning, everybody. As we get started today, so over the weekend, I think late Friday, midterm one scores posted. The average for our class was about a 76%, which I was thinking, today, like if you take the 38% of the class, which is your lab scores, your homework scores, your recitation scores, those items in the class tend to average in close to the 90% range when you take all those items together. Usually the homework recitation, very close to 100% average on those. Lab maybe closer to like 85% average. So I think we'll be probably close to a 90% average on 38% of the class. The question is, where are we going to be in the 62% of the class for exams? 14% of those points, or 14% of the total class was midterm one. If we keep averaging a 76%, the average in the class will be about an 81 to an 82%, which is very close to the B range. So I think that we can always slide that average higher if we try to. Midterms 2 and 3 do tend to be harder conceptually. Doesn't mean the scores have to go down though. But the concepts in chapters 4, 5, and 6 I think are a little bit tougher than the concepts in chapters 1 through 3. So we have to put in some good work here over the next month. Check back after midterm 2, see where we're heading then. But if we keep a 76% average, we're heading towards a B average for this class, which would almost be a record. So let's keep it going into midterm 2, midterm 3, and into the final. One thing that's somewhat helpful to keep in mind for midterms 2 and midterms 3 is that they are only over the next 3 chapters. So they're not cumulative. Of course, there are aspects of stoichiometry that come up in chapter 4 we'll see. So we kind of need to keep using stoichiometry, but we're not directly testing chapters 1 through 3 concepts again until we get to the final exam. So the final will be cumulative, but the next midterm is just chapters 4 through 6, so we can focus on the next 3 chapters. Same thing, midterm 3, just chapters 7 through 9. Okay, so let's get back into this problem here. So last time we introduced the idea of metathesis or an exchange reaction. We were looking for a precipitate to drive the reaction to actually having a change take place. We have to have something precipitate from the reaction, a solid form. Otherwise, everything's just aqueous ions, and we're not really doing any type of chemical reaction. So when we're considering a reaction between barium hydroxide, potassium carbonate, we're trying to think, when I exchange these ions here, does either barium carbonate precipitate or does potassium hydroxide precipitate? If neither precipitate, then all we would have in this case would be aqueous ions. We're mixing aqueous solutions, so these two ions here are completely water soluble. And so if we mix 2 water soluble ionic compounds and we don't produce a solid in either one of the 2 products, then the answer to that question would be no reaction occurs. No reaction can occur if there's no solid form, no precipitate form in the reaction. Now, in this case here, I think there is a precipitate. I'd like you guys to spend just a couple minutes thinking, is it the barium carbonate? Is it the potassium hydroxide? Do you need to double check the solubility chart perhaps? And then from there, can you go through the tasks of writing the full molecular reaction? I'll give us a start here. This would be writing the barium hydroxide AQ plus the K2CO3 AQ, and then considering forming our products of switching these ions out for each other, forming barium carbonate, and then KOH. And then we're using that solubility chart here to help predict whether those are AQs or solids. So let me throw it to you guys at this stage of the problem here of going from the net ionic, from this full molecular reaction, identifying the solid, and then from there going to the full ionic to the net ionic. So take about 2 minutes here, and then I'll go through the steps to make sure we're on the same page. All right, let's take a look here at this one. So we're asking this question to identify the spectator ions. To identify the spectator ions, I think the way we would go about that is to consider that full reaction like we had started with. Try to identify if we have a solid forming, and barium carbonate's insoluble in water, so that would precipitate from the reaction as a solid. So barium and carbonate, when they combine in the solution, will crash out, form a solid, our solid precipitate. KOH is water soluble, so that just stays aqueous in the solution. And so then when I think about trying to identify the spectator ions, I get those from considering the full ionic reaction. The full ionic reaction is the idea, or I'm just using this sort of thought here, that a water-soluble ionic compound fully dissociates in water. And so we're going to have the dissociation of barium hydroxide into barium and 2 hydroxide ions. So we're going to have those ions each surrounded by water. Then we'll have K2CO3, same thing, water-soluble ionic compound. So the thought here, is it an ionic compound? Yes, it is. And then if so, is it water-soluble? And then if it is, it fully dissociates. And so we get the dissociation of K2CO3 into 2 K pluses and a carbonate ion. And then I don't get the dissociation of that insoluble compound. So if we're insoluble, then we remain intact. So barium carbonate is an ionizing solution. It's solid, that's why it's a precipitate at the bottom of this reaction. And then KOH, water-soluble ionic compound, so I have the 2 K plus and the 2 OH minus. And so then for our spectator ions, they're the ones that are unchanged. So the spectator ions are the ones that are not changed during the course of the reaction. You could call the other ions the precipitated ions, or the ions that undergo some change. So the precipitated ions are the barium 2 plus the CO3 2 minus, that these ions here precipitate to form BaCO3 into our net ionic equation, or net ionic reaction. And so then the ions that are left out here are the spectator ions. So the unchanged ions on both sides of the reaction, present in the exact same quantity and amount, and are not part of the net change, are the K plus and the hydroxide ion. So potassium hydroxide ions serve as the spectators. The idea is they kind of watch the reaction take place while themselves not being changed. So when we cross these out here, this doesn't mean that they spontaneously disappear. They're still there. They're just not part of the net change of the reaction. And so the spectator ions are the unchanged ions during the course of the reaction. So we have a hard time seeing in the full molecular reaction which the ions are unchanged. Because the full molecular, we're sort of pretending like barium hydroxide exists in the solution even though we know it's really ionized. So we will write BaOH2, things like that, AQ a lot when we really have to appreciate that it's a solution of ions. We should really be thinking of a solution like this as Ba2 plus and 2 hydroxide ions. Okay, so that's how we approach a problem like the identifier ions, writing net ionic reactions versus full molecular reactions. Now let's get into the topic of acids and bases. We introduced a little bit of the behavior of acids and bases. We saw that acids are actually capable of serving or acting as strong and weak electrolytes in solution depending on the acid. We weren't yet able to predict which ones were strong versus weak acids. You might, of course, remember we learned how to name a bunch of acids. So I think we know how to recognize a big series of substances that act as acids, or that we call acids by nomenclature. Now we can take advantage of knowing a lot of acids and then try to understand their properties, and then also just take for granted that some acids will fully dissociate, and we'll just have to more or less memorize which ones do that full dissociation. And so acids are just any substance that ionize an aqueous solution to yield H plus ions. And so we saw 2 examples before. One was HCl, hydrochloric acid, reacting in water. Now we can write this reaction one of 2 ways. We can write it this way. Here we have water in the reaction, HCl. We're kind of considering HCl in this solution. How does it react with water? Well, the H plus is sort of absorbed by water, so we form H3O plus and then plus Cl minus. And we get this reaction to take place 100% of the time, meaning we get the complete dissociation of HCl in solution into H plus or H3O plus ion and into Cl minus. Another way we can write this reaction is just HCl AQ goes directly to H plus plus Cl minus. And so anything in reaction, anything in solution that's making H plus, or what we might write as H3O plus, we would call the substance producing those ions to be an acid. So we look at HCl here and say that this is just reactions that show HCl behaving as an acid. Because we get complete formation, though, of H+, we would call HCl a strong acid. And so our strong acids are things like HCl, HBr, and HI. One example, though, of a weak acid is the other halogen, the halide at the top of the series, HF. So hydrofluoric acid is a weak acid, meaning when it does this reaction in water, that we only get a partial reaction to the products. Now, it's probably about maybe 5 to 10% ionized, but for practical purposes, the idea here is that we just don't get total ionization. We get like less than 100% yield in this reaction. You might consider getting an equilibrium, meaning you have the forward reaction taking place to produce the products, then every now and then the H+ and the fluoride recombine and go back to HF. The implication for HCl is that if an H+ bumps into a chloride, that they're just like they bounce off each other and they never really reform HCl. The nature of why acids and bases behave the way they do comes up a little bit more in chapter 16, comes up a little bit in organic chemistry. So there's topics later that try to describe why certain acids behave one way versus another. This part of the class, we're just really trying to understand some things behave like HCl and fully dissociate, some things behave like HF and just partially dissociate. It's interesting for HF because it's in the group with the other halides, but just HCl to HI are strong, and then HF just happens to be weak. Now this might make you think HF's not dangerous to work with. HF is extremely dangerous to work with. In fact, HF is one of these four that I would never even touch if I encountered it in the lab. It will eat through your skin, and it can kill you with even not much getting onto your skin. So you have to be incredibly careful and get incredible amounts of training if you want to work with something like HF. Very fascinating scene in Breaking Bad. If you want to see it, feel free to go try to find it. HF, Breaking Bad. You might Google it. It's kind of gory. Those who've seen the show know what I'm talking about. But really, like, because HF dissolves skin, flesh, bone, rock, everything but plastic. This comes from the show. And so HF, incredibly dangerous to work with. Even though it's a weak acid, it can still have corrosive behavior. And so HCl, HBr, HI, not exactly great acids to work with either. They're corrosive as well. You don't want to get those on your skin either. They'll give you a burn. But HF burns, doesn't take much of a burn to actually lead to a fatality. So anyways, HCl, HBr, HI, fully dissociated in solution. There's going to be 7 strong acids. So we're going to have 7 different strong acids that we go through. The other ones would be the HClO3, HClO4, so perchloric and chloric acid. Perchloric is another one on this list that's incredibly dangerous to work with. Can make, if you add it to different organic matter, you can make things explosive and they'll just spontaneously detonate if you're not careful. HClO4, and then we have HNO3, nitric acid, and then finally H2SO4. And then a lot of times we say the first H, and we'll explain this in a minute. So just the first hydrogen, or the H+ to fall off of H2SO4 does so completely. And so that gives us 7, we often call them inorganic strong acids to separate them from, there are some strong organic acids that we don't bring up in general chemistry. You can learn about some of the strong organic acids when you take OChem. So just know that when we say there's 7 strong acids, we mean on the inorganic side, kind of on the non-carbon, the sort of non-major carbon-forming acids. And so let's look at H2SO4. So for H2SO4, the implication here is that our first step here to form H+ plus HSO4 minus ion occurs in solution with 100% yield. So we get complete dissociation here. And then the implication is that that hydrogen sulfate ion does not completely dissociate. So then the HSO4 minus ion in solution has a partial reaction to a second H+ plus SO4 2 minus. So that's with less than 100% yield. So imagine H2SO4, you have it in solution. You're going to have predominantly HSO4 minus and a small amount of SO4 2 minus. And if you're thinking about, like, say, dissolving 1 mole of H2SO4 in solution, if it were to be completely strong for both steps, you would have 2 moles of H+ ion form, and you get somewhat more than 1, but not quite 2. So you might get 1.1 to 1.2 moles of H plus per mole of H2SO4 in solution. As we get into the later parts in the chapter, we'll learn a little bit about quantifying molarities and concentration units. So we'll start to quantify aspects of these types of solutions. Though you might recall trying to calculate very precise concentrations, you might remember Kas and using a Ka to try to calculate H plus and the pH of like weak acid solutions. That's a chapter 16 problem in Chem 1220. So we're just going to look at concentrations of salts and some general reactions later in the chapter in terms of quantifying aspects of the reactions that might take place. Okay, so we see here 7 strong acids. You might recall that we learned how to name a bunch of other acids. Any other acid we learn how to name, the implication is that it's just a weak acid. And so the other acids we learn how to name, I'm not going to go through them all, but a few examples would be like acetic acid, which sometimes we write CH3COOH, or sometimes we write it H, C2H3O2, but it has this structure shown here. Sulfuric acid, H2SO4, has this structure shown, as does nitric and hydrochloric acid. Like I said, you'll talk later about what it is structurally about nitric acid that makes it strong versus nitrous acid being a weak acid. So HNO2 would be a weak acid, H2SO3, sulfurous acid. If you notice, all of the strong acids are ic acids, so hydrochloric, hydrobromic, hydroiodic, and chloric, perchloric, sulfuric, nitric. So none of the us's. So if you remember nomenclature, you can remember if something is an OUS acid, it's a weak acid. Now there's other ic acids that aren't strong, like bromic and iodic and periodic, for example. So not all of the ics are necessarily strong, but all the acids that are strong happen to be ics. And then, so we'll say here all the other acids from chapter 2 that aren't one of the 7 strong are weak acids by implication. So we just like to be able to give you an acid and say, is it strong or weak? And it's just really identifying the 7 strong. And if it's not one of those, it's just a weak acid. Okay, so some of the ways we can classify acids is if they have more than one H plus to donate to a solution. So HF, HCl, HNO2, we would call these monoprotic because they have one H plus each. And notice that we'd call an acid monoprotic even if it's weak or if it's strong. So when I look at these acids here, I have just one strong acid and the other 2 are weak, but I still would call all of those monoprotic acids. I would call HCl a monoprotic strong acid, and I would call HF and HNO2 monoprotic weak acids. So these would be monoprotic but weak acids. So a diprotic acid is any acid that has 2 H pluses to give to the solution. So carbonic acid, H2SO4, H2SO3, of course those would be diprotic acids. And again, even if not all of those H pluses are strong, we still would refer to the acid as being diprotic. Triprotics would be things like H3PO4. Well, a lot of examples of H3PO3, even though it's really a diprotic, but that's a weird story that's not worth dwelling into. So you'll often see H3PO3 on this list here. It's kind of weird. I think we should dust it under the rug. You'll see it come up maybe in the end of chapter 16 in Chem 1220. One of the H's is bonded to phosphorus, the other 2 to oxygen, and it turns out only the 2 to oxygen actually will ever fall off in water or an aqueous solution, but that's a small detail. But looking at H3PO3, you would think it's a triprotic, and that's fine if you think that here. And I think there's been questions that usually put it in the triprotic category. Another one is acetic acid, which you may not necessarily have expected or thought that we'd see something like citric acid on this list. But citric acid has kind of 3 of those acetic acid groups. In fact, let's look at acetic acid real quick, because there's something interesting with acetic acid that's worth talking about, is that only that one H ever comes off in water or if we add base to the solution. So we only have one acidic hydrogen. So acetic acid is just a monoprotic. So just the presence of H in the equation for the substance, it says monoprotic. Monoprotic is what I'm trying to write. And so these other hydrogens are non-acidic, meaning they never fall off in solution. They always remain attached to that carbon. It also means if you look at a substance that's not an acid at all, think about something you don't even know with the acid name, like methanol, for example. So if we see methanol, sometimes we get confused and start thinking, does it have 4 hydrogens that can come off in solution? It actually has 0. So think of it this way, is that an acid? Usually the thought is, well, I see an H, so it looks like an acid. But my question would be, do we know how to name it as an acid? Because if methanol behaved as an acid in solution, it probably would be called like methanol acid or something like that. It would have a different name. So this substance here is not acidic. So you throw it in water, it's still methanol. That hydrogen's still attached. It doesn't spontaneously fall off. So the only time the H falls off is off the substance we call to be an acid or term an acid. So the acids lose H pluses, and it doesn't mean all the H plus or all the H's in the acid will ever fall off like in acetic acid. Only a monoprotic, only that one H falls off, the other 2 remain intact. Kind of like they remain intact on methanol. And so it may seem confusing at first, but when you think about it, most substances H's actually aren't acidic. It's kind of rare or peculiar that an H is acidic and does fall off. And when that happens, we make sure to call that substance an acid by nomenclature so that we recognize and know that it's going to lead to those H pluses falling off. And so then when you notice for the acetic acid that it's that COOH group, is that like carboxylic acid group, it looks like a carbon double bonded to oxygen and then an oxygen bonded to hydrogen, kind of like this. We'll see this more in chapter 8 when we get through structure. You may have seen those structures already, but this is what that COOH group looks like. It's this H plus here that when it loses and leaves behind this ion here, that carboxylate ion is particularly stable, which allows the H plus to fall off. So it's like the stability of that carboxylate ion that allows something like acetic acid or things with that COOH group to be acidic in the first place. So when we look at citric acid, I have 3 of those hydrogens here. So these are the 3 acidic hydrogens on citric acid. Then all the other hydrogens are non-acidic. So we would look at all these other hydrogens. Just a normal hydrogen on a carbon is not acidic. An ordinary hydrogen on an oxygen isn't acidic either unless it's on one of those carboxylic acid groups. So we can recognize that COOH group as an acidic group. There's a question back in chapter 2, I think on a homework set that I didn't like. I think I changed it to practice points, which was getting at, is this thing here an acid? And back in chapter 2, I would not necessarily think you guys would have thought that this would be an acid just yet because we hadn't really talked about this functional group being acidic. And so that COOH group is acidic, and we can see that here in chapter 4, once we have a little bit of an understanding of acids and how they behave, and the fact that not every hydrogen in a molecule is acidic, only certain ones. Now, bases are the sort of counterpart to acids, of course. Bases are things that make hydroxide ion. And at first, that may seem strange. Maybe it doesn't seem strange. I don't know what seems strange to you guys. But water dissociating partially into H plus and OH minus is how the 2 are connected together. So why an acid is important is because it's increasing the H plus ion, decreasing the pH. When you learn pH units later in the class, you'll learn pH. You probably already learned it in bio or chemistry in high school. But pH is related to the hydrogen ion concentration. The pOH is related to the hydroxide ion concentration. And those 2 are linked together by the dissociation or their association together into water. And so things that produce hydroxide ion in solution are termed to be bases. And so we actually know a lot of things that act as bases. Those would be those hydroxide-containing ionic compounds that are water-soluble. So the water-soluble hydroxide salts, salts and ionic compounds are terms, and sometimes I'll use the 2 interchangeably, are pretty interchangeable. So you might hear me call something a salt. That's also an ionic compound. So these water-soluble hydroxide-containing ionic compounds, of course, have to produce hydroxide ion in solution by definition, just by the virtue of those solutions containing hydroxide ion. And so these would be, if you just memorize the list, would be the alkali hydroxides, calcium, strontium, barium hydroxides, then ammonium hydroxide. So these things here, you throw them into water, fully dissociate into things like ammonium and hydroxide ion. And so any of those compounds there we would term to be strong bases because they're creating hydroxide ion completely in solution with 100% yield. And then There's some substances that don't actually contain hydroxide ion that we can term to be bases. We saw one example of ammonia because we were looking at putting ammonia solution and seeing that it was electrolytic. So ammonia in water is electrolytic because we're forming hydroxide and ammonium. So we're taking the NH3 is actually removing an H plus off of water and leaving behind an OH minus. And so we form an OH minus ion. So the formation here is why we call ammonia to be a base in water. And so ammonia added to water is increasing the hydroxide ion concentration and allowing the solution to be more electrolytic, has more ions than a pure water solution has. Remember, pure water dissociates a tiny bit, but not enough to make water electrolytic. So we need to add something that increases the ions in solution. Something like ammonia does the trick. But we get less than 100% yield. And I can imply less than 100% yield if I see an equilibrium arrow. If I see a full reaction arrow, I'm assuming 100% yield. If I use this equilibrium arrow, the implication of the equilibrium arrow is we always have the forward reaction taking place and then the products recombining some of the time so that we have the products and reactants present with less than 100% yield. And so we would term NH3 here to be a weak base. Now, the thing that's kind of peculiar here is that we could go really deep here and talk about some different types of organic ammonium compounds like trimethylamine, triphenylamine, and introduce a lot of other categories of bases that look like N, that's an M. So like if we take the nitrogen sort of group and then have three things attached to it, it's still with that lone pair on nitrogen, but we don't really know how to sketch a Lewis structure yet. But if we knew how to sketch Lewis structures, we would be able to identify easily, basically having nitrogen with three things attached to it would have that lone pair of electrons, would allow nitrogen to act as a base here. But we don't easily have the ability to kind of conceptualize structures very easily. Like one example, this would be like NCH3 would also act as a base, but really ammonia becomes kind of the prototype that we use here in 1210. And we don't go too deep with other examples. If we did, they would look like things like this. And we could also go a lot deeper on other ionic compounds that just get tricky, and I don't think we want to go there just yet. Like, for example, oxides. When an oxide dissolves in water, if you think about your solubility chart, you didn't see oxides on there. And the reason why you don't see a lot of the other ions we learned how to name on our solubility chart is it gets complicated quickly, because things like oxides will react with water, and an oxide ion in water will produce hydroxide ion. So an oxide, the 2 minus, will take an H plus off of water. It actually produces hydroxide as the byproduct of water, and then hydroxide by the association product, so we get 2 hydroxide ions here. So the oxide ion is actually a strong base. So anything that makes oxide ion in solution is going to completely lead to that thing making hydroxide ion. But like I said, it gets complicated. When you start having to envision secondary reactions leading to hydroxide, gets complicated quickly. A lot of ions actually act as weak bases in water. I used to try to teach this, and it gets really tricky pretty quickly. But you can probably appreciate that things like acetate and fluoride ion can react with water to produce some hydroxide ion. You can maybe appreciate that and never, again, have to worry about predicting it. So other ions can react with water and kind of produce hydroxide ion as well, maybe not necessarily fully with 100% yield like oxide ion does. So my point here is just to say it could get much more complicated quickly. Ions can still produce hydroxide ion by secondary reactions, and we're not going to focus too much on those secondary reactions, but maybe just appreciate that ions in solution can continue to react with water. And those topics do come up later, and you'll talk about them more later. So I think let's just leave it for later to talk more about how oxide ion and some of the weak base ions behave with water. There's some like really interesting questions too of like, is ammonium, let's just leave it at that. So like, there's just some interesting problems that come up in acid-base problems that you'll see later in Chem 1220. Okay, so let's talk about the strong bases associate to hydroxide ion plus a counter ion. And so this is just what we had seen before. And so a strong base, let's give another example. That might be something like sodium hydroxide. So sodium hydroxide. We know that this is a strong, electrolyte, completely dissolves in water. So if we throw this into water, we know we're going to get the sodium hydroxide AQ because it's water soluble. And then because it's water soluble and it contains hydroxide, we know it's a strong base. We're going to completely get our hydroxide ion and our counter base sodium. And so water soluble, strong electrolyte. Strong base because it's producing hydroxide ion. So remember, an electrolyte is anything that makes ions. And then when one of those ions is hydroxide, it's a base. So we call it a strong electrolyte, strong base. And then so just making sure we see the reaction of a weak base. So the prototype here is really just ammonia producing ammonium. Yes?
Is that a two-step process, Doctor?
Well, it's I'm picturing, so the two-step process is like imagining having solid sodium hydroxide and making sure that we picture that it's water soluble is kind of the first question. So for ionic compounds, so when I look at this compound here, when it's an IC, I can predict water solubility. So water solubility is just using the solubility chart. For molecular compounds, we really don't have a solubility chart. We're not trying to figure out if HCl is soluble in water. For HCl, the question is it a strong base or a weak base, or a strong acid or a weak acid. And we're going back to what we called it hydrochloric acid, so it's an acid, and then it's strong because it's one of the 7 strong, is the sort of thought. And then for our weak bases, the prototype here is just NH3 reacting with water, and this is where we get the ammonium. This is a weird slide. I don't know why I have this slide in here, to be honest, because we kind of already wrote this reaction. So this slide here is just almost prompting us to rewrite the reactions we wrote on the previous slide. And so we're getting these ions here, but with an equilibrium, less than 100% yield. So that's why this is a weak base, weak electrolyte. Now, the idea here is it's making ions, so that's why it's an electrolyte. Partially making ions because of the equilibrium arrow. Also partially because we're kind of memorizing ammonia does this. So we just have to know ammonia is the prototype that does this weakly. And then hydroxide is one of the products, so that's where the base comes into play. That's why we call this weak electrolyte, weak base. Okay, so this table's in the book, and I actually should have looked to see if they changed this table. This is probably the most confusing table in the book. But we can break this down. I wonder, and maybe it's worth a double check, and I'll see if they change it, and if they have a slightly more useful table, I might bring it up next time. But I bet this is still in the book. This has been in the book for as long as I've been teaching. What makes this table confusing to students is that this table here is a summary of the electrolytic behavior of common soluble ionic compounds. So the table is assuming, so the only compounds that are being considered in this table are ones that are already water soluble. So if the compound is insoluble, it's not on this table. So if you're looking at calcium carbonate, insoluble, it's not considered for this chart here. So when you look at ionic compounds, for ionic compounds, remember the only consideration for an ionic compound is it water soluble. If it is, and therefore on this chart, the only possibility for the ionic compound is that it's on that strong electrolyte side. So because all ionic compounds, when they dissolve in water, dissociate into their ions. So there's no way an ionic compound's dissolving in solution and not ionizing. So there's no categories, there's no examples of non-electrolytes or weak electrolytes. Now, what would you call something insoluble? Like if you looked at calcium carbonate and said, what would we call calcium carbonate? Well, it's not a strong electrolyte because it's not in solution. You can't even call it a non-electrolyte. It's not an electrolyte is a property of something in the solution. If calcium carbonate dissolved but remained paired up with itself, would be the non-electrolyte. So that would be a non-electrolyte. It doesn't do that either. So calcium carbonate, it's not applicable to consider it. So for something that's insoluble in water, you can't give it a term that you give a solute in the solution because it's not a solute in the solution. So we can't really consider the insoluble compounds to have any kind of electrolyte behavior. I stress this because a lot of students will think that something that's insoluble is a non-electrolyte. And do you see how that's not the case? So the non-electrolytes, this isn't the case of insoluble. Something insoluble is not in solution. It's not applicable to call it any of those types of electrolytes. So for an ionic compound, if it's water soluble, it strongly dissociates into its ions, complete dissociation. And then if it's molecular, we then have to think a little bit about, well, is it a strong acid? because all of our acids, HCl, HBr, HI, HNO2, even the weak, CH3COOH, HF, HNO3, all those acids are molecular. So all acids are molecular compounds. They don't contain metals and nonmetals, just non-metallic elements. So our molecular compounds are, we have our 7 strong acids. So the 7 strong acids completely dissociate and therefore are strong electrolytes. Then our weak acids and our weak bases, which is really just ammonia for the weak base, but our weak acids and our weak bases partially dissociate in solution, are termed weak electrolytes. And then all other compounds that are molecular are in this category of being non-electrolytes. Now, it probably seems like there's not many other compounds, but there's millions of other compounds. Like, think of all the different alcohols, all the organic compounds you have. Anything you don't call an acid or a base doesn't ionize in solution. So this would be things like sugars, things like any almost other type of organic compound you can think of fits this category of being a molecular non-electrolyte compound. So let's give a few examples. These could be things like methanol. These could be things like ethane. These could be things like glucose, sucrose, and we could continue, like as long as we wanted to write compounds. So the implication would be if you see a compound that you don't recognize as an acid, you don't recognize it as ammonia or something that looks like ammonia, the implication is if it's a molecular compound, then it's a non-electrolyte. Okay, now there's one other category that you don't see that you're probably like, where is it? Where are the strong bases? Why do you not see a strong base anywhere on this list? Because our only strong bases are already in this category here. So the strong bases are already included because they're ionic. So calcium hydroxide, sodium hydroxide, KOH, those things are ionic compounds. So they're already assumed to be water-soluble, strong electrolytes, and their electrolytic behavior is being included in the category of ionic strong electrolytes. So that's why you don't see strong bases on the chart, because they're already included in the group of compounds that are in the ionic strong electrolyte side. Okay, so just remember, an electrolyte is any substance that dissociates into ions in solution. Strong electrolytes completely dissociate, and then non-electrolyte doesn't dissociate at all. Weak electrolytes somewhere in the middle. Somewhere less in total ionization for our weak electrolytes. Other than just having a couple examples, that's kind of the first half of chapter 4. So let's look at a couple examples to try to wrap up some things and some details from chapter 3. So let's come back to a really simple, I think this is a pretty simple question. What solute particles are actually in the solution for each of the below compounds? For KNO3, just remember here, this is just the K plus and NO3 minus. We almost started with an example like this, and it's just really making sure that we still see nitrate remains intact. It doesn't fall apart and dissociate further. K plus remains as the K plus ion. So these are our only solute particles in a solution of KNO3. If you have HNO3, remember the thought is strong versus weak. Is it a strong electrolyte or is it a weak electrolyte? Strong electrolyte, so we get H plus and NO3 minus. And you could write that H plus as H plus or H3O plus. I prefer H plus, but sometimes in the book or other examples you might see H3O plus. So just remember that H plus and H3O plus are synonymous with each other. Now, what solute particles exist for HF? So if you had a pair of like molecular goggles and you're looking in a solution of HF, what do you think you're going to see? H plus and F minus only? Or do you think you'll also see some HF? You would see all three, right? So for HF, we'd have HF present, some F minus, and then some H plus. So you'd see all three solute particles. So methanol, this is a good review here. Like, how many solute particles do you think you see in methanol? Different solute particles. If you think 3, then just remember, methanol's not an acid. If you think 2, it's not a strong acid. If you think 1, you're probably right. So the only solute particle in the methanol solution is methanol. So no dissociation here. Remember, it's not acidic or basic. So we don't get any additional solute particles, just the If methanol is mixed in water, we just have methanol dissolved in water. And then lastly, on this chart here, acetic acid is like HF, so we should have some acetic acid molecules from the weak acid, acetate ion, and H+. Let's do one last one for ammonia. Just to summarize for it, we'd have the weak base ammonia, and then the products ammonium, and hydroxide ion. So the thought here is just weak versus strong electrolyte, and it's almost just going back first to, is it ionic or molecular? It's ionic, solubility chart. If it's molecular, the question is acid or base, or neither. All right, let me throw this question to you guys. So which compound below are strong electrolytes in water? It'll take about a minute for this one. So this question here, hopefully is just kind of a catch-all, just making sure that we're seeing things the same way, but it's just KOH here, because this compound here, water-soluble, strong electrolyte, ionic compound. So the thought here is if it's an IC, is it water-soluble? If it is, it's a strong electrolyte. For PBI2, it's insoluble, so ionic compound, but insoluble, so not any form of electrolyte here. Methanol is non-acidic, non-basic, so it's neither it's not a strong electrolyte, certainly not even a weak electrolyte. And then a solution of acetic acid would be weakly electrolytic, because we have the weak base. So not a strong electrolyte. So only KOH is a strong electrolyte here. Okay, so the last thing, and actually this slide probably could have been backed up a little bit in terms of almost coming after the review of the first 3 sections of chapter 4. Let's make sure we know how to write some of these neutralization reactions of acids and bases together. Because when we have H plus present in solution, we have OH minus present in solution, we're going to form water. And so the implication is if you have H plus and OH minus in solution here, the solution of HCl is really H plus and Cl minus ions because it's a strong electrolyte. The KOH solution is really K plus and OH minus ions, that when the H plus and hydroxide bump into each other, they're going to form water. And so the formation of water is going to drive these reactions to taking place. So we take 2 salts, an acid and a base. Those 2 salts will react in water to combine to form water liquid. And then plus our counter ions. So we'll form the salt here, product of NaCl. So the product of an acid plus base is a salt plus water. So an acid plus a base goes to the salt plus water. So now water is the driving force of this reaction here, kind of like the solid precipitate formation was in the metathesis reaction. It's the formation is something that when you form it, it doesn't go backwards, is what allows a reaction to take place. If water completely dissociated, we'd have no reaction taking place. We just have a solution of ions still. But our solution of ions is changing due to the formation of water. Yes? Oh, sorry, it was KOH. I switched out the K for sodium by accident. Good catch, thank you. Yep, so KCl would be the salt that forms. And now let's think a little bit about the full ionic reaction versus the net ionic reaction here. And so our salt K plus is really ionized here to K plus and Cl minus. So if I was writing my full molecular reaction, I'd have HCl plus KOH goes to H2O plus KCl, just in the full molecular form. In my full ionic form, I'd have H plus Cl minus plus K plus hydroxide ion goes to water, liquid, because water liquid is a non-electrolyte. Like the very tiny amount that water dissociates isn't enough for us to call it even a weak electrolyte. So water ionizes to such a small extent. It's important you get a pH of 7, if you remember, for water. So you do create some hydroxide ions, but that concentration is 10 to the minus 7 moles per liter. Really, really low concentration. So water is not really behaving as any type of electrolyte in water. And then our K plus and Cl minus would be our product ions. So if you see here, our K plus and our chloride are unchanged in the reaction, and would be our spectator ions. So our spectator ions can be canceled out into the net ionic equation, which would be H plus hydroxide ion goes to water. And so it's that formation of that non-electrolyte water that drives this reaction to taking place. Now that's the strong acid, strong base reaction. You might wonder, well, what if one of them is weak? What if I have a weak acid plus a strong base? What reaction takes place for those? And the answer is still the complete reaction to the products. So if I'm writing this out here, I would get the salt here would be KNO2, and then water as my product. Still 100% yield. Water in the liquid state, KNO2, water soluble. Anything containing potassium is water soluble. So if I had to write a full ionic reaction for this reaction here, I'd have HNO2 still intact. I'm considering these reacting in water. Now, why would I not dissociate HNO2 into H plus and NO2 minus? I don't dissociate here because it's a weak electrolyte. I'm only going to dissociate into a full ionic equation things that are strongly electrolytic. So it's not a strong electrolyte, so I leave this intact here, just like I leave water intact, just like I don't dissociate an insoluble precipitate. So NO2AQ plus K plus hydroxide ion goes to H2O. Let me write the K plus NO2 minus first. So I get my ions plus water. And so the only spectator ion here is potassium. So it's interesting that you can have just one of the ions be a spectator ion. You don't have to have two ions be spectators. So the K plus cancels itself out. And then my net ionic reaction would be HNO2AQ still intact because HNO2 is not a strong electrolyte. It didn't fully dissociate, so I don't fully dissociate it in the reaction. Plus hydroxide ion goes to NO2 minus plus water. Our reaction should still be balanced. If it's not balanced, we may have made a mistake somewhere. Sometimes we may forget to balance things here, so we want to balance our full molecular, and everything was balanced here 1-to-1, so we were good to go, so we're still balanced here. The next reaction is one where we're going to have to balance this reaction out. So if I have a triprotic acid plus KOH, the triprotic acid just loses all three H pluses, so this really is just the consequence of losing all three H pluses here. So the product here is going to be K3PO4 for having lost all three H pluses, replace them with potassium. This is really just an exchange reaction, just like metathesis reactions were. So we're getting K3PO4, still water soluble ionic compound. All potassium salts are water soluble. And then my byproduct here is hydroxide ion plus H plus 3 times. So I'm making 3 moles of water. So we need 3 KOHs. That gets me the 3 OH minuses to react with the 3 H pluses. And so then when I think about my net ionic reaction, I go full ionic, but I leave H3PO4 intact, again, because this is a weak electrolyte. I only dissociate strong electrolytes in my reaction. 3K plus 3 OH minuses from the 3 KOHs, 3K plus, PO4 3 minus, and then the 3 waters still intact. So this is another case here where the only ions that are the same are the 1K pluses, so or the 3K pluses on both sides. So the 1 ion of K+. 3 of them on both sides cancel out. So my net ionic reaction would be H3PO4 plus 3OH minus goes to PO4 3 minus plus 3 water. So these are my net ionic reactions here for those 2 reactions. So just make sure to balance the reactions as you go so that we get the proper balanced reaction. Okay, so those are writing some acid-base reactions. So just remember, even the weak acids fully dissociate in the presence of base. And then the idea here is the non-acidic H's don't dissociate with base. Everyone's getting antsy leaving, but we still got a couple. Okay, so the first 3 sections of chapter 4 were on general properties of solutions, precipitation reactions, and acids and bases, and neutralization reactions. The next 3 sections are on these redox reactions, so reactions involving oxidation and reduction, and then talking about concentrations of solutions, and then doing some stoichiometry problems with solution problems. So getting into some problems as we go throughout the chapter. Now let's just introduce these redox reactions so we can build from these next time. So an oxidation-reduction reaction, in fact, I think it's good to hear this twice. What do people remember for what does it mean to be oxidized versus reduced? There's usually 2 things that people remember, either oil rig or Leo, the lion goes grr, are the 2 things you might remember. Oxidation is losing electrons in a reaction, and reduction is gaining electrons. So oxidation, losing electrons in the reaction. So oxidation is losing electrons, and then reduce is gaining electrons. So gaining electrons is reduction. Whoops. I'm trying to write rig. So reduction is gaining. So oxidation is losing electrons during a reaction, and reduction is gaining electrons in a reaction. And so the reaction they have shown is calcium metal reacting with oxygen O2 to produce calcium oxide. So calcium oxide, of course, has the charge states of 2 plus for calcium, 2 minus for the oxygen. So we're taking calcium from a 0 charge state to losing 2 electrons. So calcium lost electrons in the reaction. Because it lost electrons. So oxidation is losing. Calcium went from calcium with a 0 charge to calcium with a 2 plus charge. So that's it losing 2 electrons to get to this charge of 2 plus. So this also makes us remember that what we're changing to go from calcium uncharged to calcium 2 plus are the electron counts. So we're not changing proton counts. So calcium always has 20 protons, the atomic number of calcium. So calcium 2 plus has lost those 2 electrons. So losing those 2 electrons is oxidation for calcium. And then oxygen picking them up, oxygen goes from having a 0 charge in O2, so oxygen's uncharged elementally, and then when it goes to O2 minus, it absorbed 2 electrons. And so in this reaction, oxygen is reduced. So calcium is oxidized, oxygen is reduced. The 2 reactions have to tandemly occur. So one cannot occur without the other. We cannot spontaneously create electrons, so we can't have oxygen gain electrons if something didn't lose them. So we have to have a balance of our charge during a reaction. And so these reactions are often called redox reactions to imply that you have to have the reduction and oxidation simultaneously taking place. And so redox reactions are just reactions that involve a change of charge state of the reactants and products. What you can imagine comes next is the bookkeeping system on oxidation numbers, so that we can understand how do you know what the charge is, what the oxidation numbers are for atoms in their elemental form, which are going to be 0 charged, and then some other charge state when they make compounds. So we'll get into oxidation numbers on Wednesday. All right, guys, that's it for today. One thing real quick, sorry for a last announcement. I wanted to mention this at the start. Exams will be released on Friday for you to review. So that you will see your answers and the questions on Friday to the exam. So if you wanted to check your exams later in the week, you'll be able to do that. All right, guys, have a great day.